All right, guys. So we have a new chapter, chapter 9. And so technically there are two chapters actually, 9 and 10 combined. So generally 9 and 10 are, basically related to one another in such a way that 9 gives you introduction to rotational motion and 10 gives you few applications. And what I usually do here, I combine them together because 10 is relatively short. I only cover the angular momentum in the chapter. So I'm going to finish 9 and I'm going to basically do the chapter 10 as well, where I mostly concentrate on angular momentum. So that's why I kind of always have this chapters 9 and 10 combined. So that means chapter of the week going to be two chapters, or you can think like chapter and a half, right? Chapter 9 and chapter 10. All right, so this chapters gives us introduction to a rotational motion. So we're going to study angular velocity, angular acceleration, and the key here is, you know already about velocity and acceleration, but here we are looking at angular velocity, angular acceleration. That means those are not the same velocity and acceleration we studied before. Those are, you can call them linear velocity and accelerations. So these ones are angular velocity, angular acceleration, and those are mostly used for the rotating system. All right, so that means we're going to be looking at new system or defining parameters of this new system, where the system now not only moving in a straight line or let's say turning, but also rotating. Let's say think of like a airplane blade, right? So like rotating, or you take like a meter stick and rotate, or you have a disc there's rotating, right? So a pulley there's rotating. That means things that have mass and size and basically have rotation with respect to some kind of axis. So let's say a disc can rotate with respect to a center, and you can use that as a pulley, for example. All right. So that means we have two different systems that we're going to be considering. One is that something we learned, from chapters 1 through chapter 8, which is going to be sort of like a linear system. So those are the same, displacement, velocity, acceleration, force that we learned before. We call them now linear, okay? Because they make the object move in a straight line, or basically in such a way that it doesn't give it a rotation. Sort of like, let's say there was no rotation we considered. But now when there's a rotation, one thing we can see here is I can still use linear, variables to describe the motion, but it's much better to use angular variables or angular quantities to describe a rotating system, because there are certain advantages in doing so. And I'll talk about those advantages. All right, so also we're gonna then apply some of the things like, kinetic energy of the rotating object, or the momentum of the rotating object. So that means we're gonna look at some of those applications in terms of, energy and momentum and things like that. All right, so first thing you wanna have here is to understand the rotation, or, rotating object. We're gonna be looking at a different type of object now. This is not a point mass, not a particle anymore, because particle has no rotation, right? Particle has no size, so it cannot rotate. But when you talk about object that can rotate, so let's say, for example, you can have a meter stick. Now it's an object, it's not a point particle, because I can make this meter stick rotate with respect to its axis. So let's say it can rotate like this, right? Counterclockwise, or it can rotate clockwise, right? That means you can have a rotation with respect to this axis. Or I can have a rotation with respect to, for example, the center, or with respect to the one of the ends, right? So maybe like now I have this end is fixed, and instead of rotating with respect to center, I can have it rotate with respect to, one of the ends. Or maybe it's a disc. Well, in order for the disc to rotate, it has to have a mass. Radius could be a sphere, like a ball, right? If the ball was rolling, or, because it has a size, right? So, and those are the things we have to consider, not only the mass, but also the size, which is the radius. All right, so usually those type of objects are known as rigid objects, okay? That means, assuming that when it's rotating, you cannot, there's no deformation. So that's why the rigid object is one that is non-deformable, because when it deforms, the rotation is much, much more complicated. So we don't want to, we don't have some kind of, deformation and things like that in our problem. All right, so the relative location of all particles making up the object remain constant. That means, for example, this is a meter stick, which is, you can think like, okay, it's one object, but technically meter stick is, combination of trillions and trillions of, mass particles, right? So that's why we can say that relative location of all particles making up the object remain constant, okay? That means, let's say this object is not gonna, let's say this object, or this particle in this object will not be moving to the left, because let's say if some of those particles here move to the left where nothing is moving to the right, then you're going to have a non-uniform distribution of mass particles, right? And that makes it, again, a little more complicated. That means we're going to assume that it's a uniform distribution of masses or the particles inside the object. And so that's why we can say it remains constant. Okay, so all real objects are deformable to some extent, okay? That means, there is really no such thing as ideal rigid object. But one of the things we can say here is, as always, we can simplify a little bit. We can simplify to the point where we can say that if there is, a deformation, right, it's negligible. So we can ignore it. That means it's almost like ideal, and we can just go ahead and use it in terms of, a perfect rigid object. All right. So one good example that we can use for a rigid object is just a, CD, compact disc. So imagine that you have a CD and it's a rigid object, again, assuming that there is no deformation, it is moving. And we're going to assume that it is rotating with respect to the center. So O represents the origin, right? That's basically that. Now, if any rotation is going to rotate with respect to that. Okay, so it's fixed with respect to its origin. Okay. Now, what we're going to do here is we're going to have a motion. Now remember, every time there is a motion, the best way to approach that is to have some kind of reference, coordinate system. You have a coordinate system and you have a reference point, or, in this case, it's going to be actually a reference line. So think like this. So, we're going to use just same Cartesian coordinates that we did before, where I'm going to say that this is the x-axis, this is the y-axis. Okay. But on top of that, we're going to also use, polar coordinates, because we're going to see, right, the rotation kind of combines both of those things, and generally it's a little bit easier when we use polar coordinates. All right, so remember that in terms of then what we have here is this positive x-axis, right? You can see, right? So this positive x-axis then becomes my reference line, not the point, right? So remember, before it used to be the origin is a reference point. So here we have a reference line. That means the entire positive x-axis is our reference line. That means if I'm considering some kind of, a particle in this, object that's at position P, right? You can see, right? That position P represents a position of some kind of, object, okay? Or the, sort of particle in that object, which has a distance r from the center of rotation or axis of rotation, okay? That means what I have here is maybe like, let's say I can say this radius r, big R, is the size of the disk, right? The compact disk, but the lowercase r is the position of that particle P on that, on the disk at, let's say, and that P, let's say, represent its position. Now, one of the things that I can have here is this, right? So again, so we choose a fixed reference line, and we have then point P is at the fixed distance r from the origin, okay? Now, if I start rotating this, that means the disk start rotating, I am restricted to kind of two types of rotation. One, rotation of the disk clockwise. Another one is a rotation of the disk counterclockwise, right? That means the disk basically can rotate, counterclockwise. That's right. Or it can rotate clockwise. Okay. That means this point P either going to start going counterclockwise like this, right? Or let's say our opposite direction counterclockwise. Now, as always, in terms of, if you remember, right, whenever you had just a regular Cartesian coordinate system with a linear motion, let's say here's my object, and let's say this was its position x initial, I would want to say, okay, so if it's moving in one direction, let's say to the right, compared to another direction, let's say to the left, the easiest way to, separate those different type of motion to the right and to the left by making one positive, the other one is negative, right? Remember, we said that if you're moving to the right, then your displacement here is positive delta x. That means you're moving in a positive direction. So if you're moving to the left, then your displacement is negative x, because now you have a negative displacement, right? And that was just basically, this negative just represents that you are moving to the left. Well, same thing is here. So you have clockwise and counterclockwise, right? Again, we'll come back and summarize this, but think like this. One direction is exactly the opposite of the other direction, right? Or one type of motion. Well, by convention, we take counterclockwise to be the positive direction and clockwise to be the negative direction. That means if the particle, right, or this disk is rotating counterclockwise, then we say it's a positive direction motion. Clockwise gives us a negative motion. All right, so point P will rotate about the origin in a circle of radius r. That means as this disk starts rotating, let's say counterclockwise, then you can imagine, right? So this point B gonna start rotating and moving with the disk, because it's a fixed point on the disk, right? So it's gonna start moving like that, okay? As is a function of time, as it's moving, it's gonna like basically rotate about the origin in this circle of radius r. Okay, so it's gonna rotate like this. All right, now how about the other particles on that disk? So let's say, how about something right here, or something right there, or something like this? Well, as the disk is rotating, every single point gonna undergo, same type of circular motion. Okay, that means every particle on the disk undergoes a circular motion about the origin O, right? And everything, is basically done at the same time. That means as the disk starts rotating, every single particle in that disk gonna rotate together, right? It's not like this, let's say this P1 gonna move, P2 gonna stay there, right? No, the disk is rigid object. That means we assume that if the entire disk is rotating, that means every particle, right? P1, P2, P3, right? They're all rotating together. Now, let's say, all right, so let's say this was our particle. This was initially at that position, right? Remember, on the reference line. And this is how we represent counterclockwise motion. So just an arrow like that. We say that, okay, so now the motion is counterclockwise. Remember, and that's a positive direction motion, right? Okay, so then what I have here is this. This particle moves from this position, right? You can see, right, it undergoes, circular motion. It gets to this position P, and let's say I freeze the frame. That means, I'm looking at, instant when the particles goes from, let's say this point 1 to this point 2, right? From the point 1 to point 2. Okay. Now, how can I represent that, motion? Remember, one of the things we have here is, again, analogy giving you from the linear motion. So let's say if you start from here, you move over there, then we could say, okay, so this is your displacement, which was x final minus x initial. Okay, so then how do we represent that type of, displacement for the rotating system? Well, there are several ways, and we're going to talk about that. So you can see right now, as particle moves, the coordinate that changes, the only coordinate that changes is theta. Because one of the things I can say here is the angle theta with respect to reference line now has increased, right? So you can see, right, it increased. That means we can say that it undergoes some kind of angle theta displacement. All right, so technically there's another way I can represent the displacement. I can also represent it with arc length S. Remember, that means what I have here is there is this linear displacement, which is my arc length here, but there's also angular displacement, which is in terms of theta. Okay. and they are related to one another. So the arc length and theta are related because there's equation, right? That relates those things. We're going to see that, in a minute. So that means the arc length is proportional to theta. Now, what do I mean by proportional to theta is that as arc length increases, theta increases, right? And more it increases, let's say more theta increases, and so on and so forth. That means they're proportional linearly. Okay, so again, here what we're going to do is we have option. We can represent linear motion of that point, or we can have then angular motion of that point. Now, how do I measure the linear motion or the displacement of linear motion? In terms of displacement of the arc length, right? By how much that linear distance. Again, kind of come back here. Let me kind of represent. So as you move from this point 1 to this point 2, this represents the arc length. This is the arc length by how many meters or centimeters, right? But it's a unit of length. It moves with respect to point 1. Okay. But I also can do the same thing in terms of the angle theta. Okay. Angle theta can also allow me to represent same displacement. That means whenever I'm doing angular motion, you're going to see I'm going to be doing in terms of changing this theta. Okay, so that's why polar coordinates are convenient to use to represent the motion of P or any other points. Because here's the thing, for example, let's say in terms of freezing at this point 2, I wait until it moves here and then I freeze. Let's say this is point 3. All right, so what is then linear displacement? Where linear displacement is, you can see, right? So this is exactly half of the circumference. So I can say that this is half a circumference. How about in terms of angular motion or angular displacement? Well, we know that this is exactly, half of the full rotation or full cycle. And if you remember your, the unit circles, right? So we can represent in terms of radians. So this is 0 radians. So let's say this will be pi over 2 radians. This is pi radians. So let's say here will be 3 pi over 2. And this will be then coming back to 2 pi radians. That means same way I can say that my displacement is pi, and you know exactly what it is, right? What if I say it's pi over 2? That means you know what it is. 3 pi over 2 or 2 pi and 5 pi over 4, even whatever, right? You will always know the position, when I represent it in terms of, polar coordinates or angle in terms of that. Okay. Now, so you can say, right? What I can do here is I can say P is located at R. R is the distance of that point P relative to the, axis of rotation. Okay. And that means, for example, right? So if this is that point P and this is the axis of rotation O, then R represents how far away it is from the axis of rotation. So then if this point P undergoes, let's say, this much displacement, then I can say that it is located R, and right now the position is pi over 2 because right now it's here, right? This is my point of interest. That means you can always represent it in terms of the polar coordinate, and we can figure out where the object's position is. All right. Also, you can see, right? So where R is the distance from the origin to P, and theta is measured counterclockwise from the reference line. Remember, the reference line is kind of equivalent to, like, let's say, origin in a linear system. And the linear system has just a point. The angular system has a line as a reference. So that means from the reference line, which is positive x-axis, how many degrees did it move? 10 degrees, 20 degrees, 90 degrees. Or we can, one thing you're going to see, we're going to start, instead of using degrees, we're going to start using radians, right? Pi over 2 radians, pi over 3 radians, 2 pi radians, 10 pi radians, right? That means, still can give us that same, let's say, displacement, right? And again, remember the arc length, which is linear displacement of the particle, and the angular displacement, theta, right, are related using this arc length equation, okay? Remember that you can see from here that S is proportional to theta, and R is just the distance of that point of interest with respect to the origin, right? Or the, you know, the axis of rotation. All right. So this equation gives you the, you know, arc length. Remember, so this is arc length. This is arc length, and it has units of meters. The radius, or not the radius, this is the distance of the particle, is also in terms of in meters. So then technically, theta has no units. It has no units, but we use radians as units of theta. But let me tell you this: theta, when it has units of radians, or even when it has units of degrees, right? Those are dimensionless quantities. Those are kind of like made up quantities that we use. Because here's the thing: if this is meters, on the right side, meters times anything else, not going to work, because, you know, distance already in meters, and the left side is, you know, meters, you know, that's it, you're done. But you're also multiplying, you know, R with theta. That means theta has to be some kind of unitless quantity so that left and right side agree with units. Okay, so then you can see, right, that's how those are related. This is the same equation, you know, written a little bit differently. That means you divide both sides by R. In a way, you can see that this represents, let's say, if, for example, you start from here, which is distance R from the you know, reference position. That is, think like this: this is axis of rotation. It's fixed. You know, your system fixed at that point, and it's going to rotate with respect to that point O. And if you start from this position, then you can represent it two different ways. You can say this is my theta initial, all right, or this is my, you know, linear position initial, right? That means what I have here is things like this. So for example, if you undergo this displacement, okay, that means what you have here is there's a delta S, which is the linear displacement. What is the linear displacement? Well, linear displacement is, you know, for one cycle, we learned that that's the, you know, distance covered, right? Linear distance covered, and that's the circumference, 2 pi times R. Okay, so that's my delta S. Then how about the delta theta? Where delta theta is equals to, so you can see right here, I can put delta here and the delta other side, and it becomes the same thing, right? So that means, you know, you're looking at delta theta as delta S divided by R. But let's say for one cycle, delta S is 2 pi R, and then you divide that by R, and then you can see, right, that delta theta for one full cycle is equals to then just 2 pi, which is, you know, something that you should have known at this point, right? So when you go around one time in radians, that's a 2 pi, you know, displacement. And you can see that from this particular equation, right? All right, so then one of the things we have here is sometimes the theta will be given in terms of degrees, and you need to, like, let's say, convert it to radians, but the units for theta, which is a pure number, is in radians again. So let's say when I give you theta is equals to pi, remember, it's just a number, right? 3.14. Let's say it's good enough, but it has no units. There's no units. So we, invented this units of radian, right? And just, attached to the theta, because when you see 3.14 or see a number 6, number doesn't mean anything unless it's, you have some kind of units, real or even fictional, that kind of represents what type of quantity you're dealing with. So if you see, let's say 5 watt, right? But if I say 5 radians, that means when I'm talking about theta, okay? Because radian is units of angular, position or angular displacement, okay? All right, so whenever you're given theta with, in terms of degrees, then you can always understand that, for example, right? So they're related, right? So let's say if you start from here, go, half a cycle, then that's 180 degrees, right? 180 degrees. But also, that means, let's say, same thing can be represented as pi radians. That means you can see, right, theta in radians is, same as, pi divided by 180, because that's the equivalent, right? Pi radians is equals to 180 degrees. So you can always use this conversion factor to go from radians to degrees or from degrees to radians. All right. Also, one of the things we have here is if you have a disk, there's rotating with respect to its center. So remember, this is a solid disk, right? Rigid object, solid object. When I'm saying that, let's say one particle undergoing, let's say 2 pi displacement, that means every particle in this disk undergoing 2 pi displacement exactly same time, okay? They all move together. They all move exactly same displacement at the same exact time. All right. That means one thing we can do here is this. Whenever the object is, undergoes rotational system or rotation, I can talk about its motion in terms of an angular variables. And let's say I can start, representing its initial position and final position, right? In terms of angular positions, okay? Again, I will eventually show you, let's say, why there are advantages on using this, right? But right now, think of it like this. Using the angular position, right? You can represent object's displacement with theta in radians, okay? Where you take the positive x-axis as your reference line, and then your theta increases if you're moving counterclockwise. That means that's my positive direction. And then you can say that there's a negative theta, right? If your system is moving clockwise. So when you say that my displacement is pi over 2, that means it moved counterclockwise pi over 2. When you say my displacement is negative pi over 2, that means it moved, clockwise, pi over 2 displacement. All right, so here's, for example, how we can set it up then, this angular displacement. So you have a particle, here's the particle at position A, at t initial, at time t initial, okay? Now, with respect to, you can see, right, a reference line, that position has, the particle has a position at point A as theta I. That means, I don't know, maybe let's say pi over 4 or something like that. Okay. And then it would go from point A to point B at some later time. And then this represents a displacement, right? Now, sorry, it represents its position, when it gets to the, position, let's say B, okay, position B. And maybe that position B here, right, is, you can say, right, that's my theta final. Maybe that's, let's say, I don't know, pi over 3 or something, okay? And then what you do here is you find their difference, right? You find their difference. And you say, okay, so my displacement is taking my final position and minus my initial position, right? So you just basically do that. And you can see, right, in terms of your displacement, you're going to get this angle. So this is your delta theta, okay? Because you undergo this much displacement. Again, same way I can say that I undergo this much in, the linear displacement, delta S, okay? But, we want to work with angular displacement, right, rather than linear displacement, which will be a little bit, obvious in a little bit later, okay? But right now, we want to say that if an object undergoes some kind of, rotational motion, right, its position change can be represented in terms of angular displacement. And that's given with respect to, delta theta, okay? Now, remember again, theta here is in radians, right? So you can say this is the angle that the reference line of length r sweeps out, okay? Now, one of the things I can do here is maybe I can also measure this T initial and T final. And if I T initial and T final, maybe I can then do the difference, right? Or, divide them, basically find the ratio. So this is my displacement, theta final minus theta initial, divided by time interval, T final minus T initial, which is basically delta theta over delta T. And this ratio just gives you how fast the object undergoes that angular displacement. All right, so just like very similar to would have been, let's say if I would do delta x, delta t, right? Linear displacement over time, remember that was average linear velocity. So this was linear, right? So now what we're doing here is we're saying that now we have angular average, or average angular speed or velocity. And that is in terms of taking the angular displacement and dividing by the time interval. That means, for example, let's say your object undergoes, I don't know, 4.5 radians displacement. All right, so 4.5 radians. Well, let's say it took, I don't know, let's say 2 seconds. Okay, 4.5 radians in 2 seconds. Well, you can see right from here, your average angular speed will be 2.75 radians per second. Okay, that means 2.25. Okay, so 2.25 radians per second. Okay, that means every second it undergoes 2.25 radians. And since this was positive 4.5, that means, angular speed is positive 2.5. What do I mean by then positive 2.5 radians per second, angular displacement or angular speed? Well, positive means that this object undergoes counterclockwise, rotation. Because if omega is positive, it's a counterclockwise rotation. If omega is negative, it's a, clockwise, all right? So, and the units are, as you can see, right, is radians per second. Again, so let's summarize. Angular speed, positive if theta is increasing, which means it's in a counterclockwise direction, and negative if theta is decreasing, which is clockwise. Kind of very similar to the linear, right? When we would have said like speed is equal to negative, or velocity equals negative 20 meters per second, means, let's say you put the x over there, that means it's a horizontal velocity, 20 meters per second speed, and negative the direction, that means moving to the left. Okay, same thing is here. You can say if omega is equals to negative 5 radians per second, that means it's the object that undergoes, clockwise motion at the speed of 5 radians per second. All right, that means, you have now kind of two quantities, right? Angular displacement and angular velocity. Okay, so again, kind of summarize. So you have delta theta, which is angular displacement. If I divide it by time, then we get angular velocity or angular speed, but it's average because you're doing displacement over time. All right, so now one of the things we can see here is this. So for example, what if my, let's say, displacement is uniform? Remember there was this uniform motion in a linear system that we considered. Uniform motion, that meant, speed, right, or velocity of the object, like V1, V2, they're all constant, right? That means you have no change in velocity. That means if I would have done this equation, V average equals delta X over delta T, I can then just ignore this V average because there is no such thing as average, because V1 is same as V2, same as V3. So then I could have, this is as a, speed, right? Average speed is the same as any other speed. What it gives me then is a uniform motion. And there was this equation, remember? Equation for the uniform motion where we could say that delta X is equals to V times T. Okay, let's say Vx times T, for example. That means there's no acceleration and object just undergoes a constant uniform motion. Same thing I can have it here. If omega average is equals to delta theta over delta T, but every second, my, let's say omega 1, omega 2, omega 3, they're all the same, then I can say omega is then constant. So I have then this equation, rearranging that I could find the displacement by taking omega, constant omega, times time. That means this is equation for uniform angular motion. Which means my angular velocity does not change as a function of time. Basically, it always remains constant. Okay. Very similar to the uniform motion. Okay, so then what happens when, let's say, your omega changes? Okay. Well, if your omega changes, then all bets are off, right? That means you have a, angular, change in velocity. That means, let's say, for example, omega final is not equals to omega initial. Okay, they're not equal to one another. So that means you're either speeding up or you're slowing down. Okay, so if you speed up or you slow down, that means you have a non-zero, change in omega, which is omega final minus omega initial. So here you can see, right, if it's a uniform motion, my delta omega has to be 0 because omega 1 and 2 or final initial are the same. So if I do change in omega, I get 0. But here I don't get 0. That means I have, a non-uniform motion. So this is going to be, let's say, non-uniform motion. All right, so let me kind of clean this up. That means what we get here is non-uniform motion. And with non-uniform motion, then we can have an acceleration. But this time the acceleration is not linear, but angular acceleration. Because what we're doing, we're considering the change in angular velocity as a function of time. Right, so then that ratio of change in angular velocity as a function of time, or delta omega delta t, that ratio is defined as angular or average angular acceleration. And we use Greek alpha, sort of Greek alpha, to represent angular acceleration. All right, now the units are radians per second squared because it's angular velocity, which is radians per second divided by seconds, right? So radians per second squared. Again, because a radian is not a real unit, so technically it can also be second to the negative half, right? Or 1 per second squared, because second is, a physical quantity. It's actual, time of measurements of time, but the radian is just a fictional measurement that, we don't really, have any physical meaning for that. So, all right, so that means what we have here is kind of like, let me come back here. So to summarize, some of those things, you have, remember, we had linear, and now this is angular. All right, so for the linear, we had displacement given in terms of delta x. For the angular, now we have a displacement given in terms of delta theta. For the linear, we had speed or velocity given with a v, which was delta x over delta t. For the angular, well, it's average, right? For angular, right, if you take delta theta and divide by delta t, then this is average omega. Well, then if there was a change in velocity over time, remember this was our linear acceleration. And same thing, if you have a change in angular velocity over time, then we define this as angular acceleration, okay? So you have linear system with displacement, velocity, and acceleration, and angular system with displacement, velocity, and acceleration, right? So you have angular velocities and angular displacements and angular acceleration. So those are the new quantities that we are, we're going to start using in this chapter. All right. Now, one of the things we're going to be able to see here is under which conditions, let's say the object undergoes positive, let's say motion, or positive displacement, or positive change in, velocity, and under which condition there's a negative, let's say displacement and things like that. Okay, so let's start with, let's say this one over here. So we'll start with this one. One thing you can see here is there's a wheel that rotates counterclockwise. All right, so as we said, right, if there's a counterclockwise rotation, means that displacement, angular displacement is positive, okay? So angular displacement is positive. Well, if the angular displacement is positive, so if you take a angular displacement and divide by delta t, because delta theta is positive and you divide by delta t, well, omega is positive, which should make sense, right? That means omega positive, you represent with an arrow like that, means you have a counterclockwise rotation. Counterclockwise rotation, right? So counterclockwise rotation is positive because you are moving in a positive direction and your position change is positive. All right, so, well, now let's look at this one. You are, or the wheel is rotating clockwise. So clockwise rotation. Well, clockwise rotation means your displacement is negative because you are going in a clockwise direction. Well, if your displacement is negative, and if you take displacement over time, well, your omega is negative. Okay, that means counterclockwise rotation is positive, clockwise rotation is negative, which gives you positive and negative omegas as well, respectively. Okay. Now, for example, then let's continue to the understanding, rotational motion in terms of the changing velocity, angular velocity. So for example, you have this, diagram for the rotating objects. So in which direction it is moving? Well, the arrow for the omega, you can see, right? So this is the omega. It tells you that it's a counterclockwise rotation. Why is it a counterclockwise? Well, because it gives you the direction of the omega. And if omega is counterclockwise, right, basically that means you have a counterclockwise positive, rotation. Okay, so, but for example, that omega 1 is at time t1. How about at later time, so this is the later time, right? You are given omega 2 with a longer arrow. Well, what it means here is that omega 2 is greater than omega 1 in terms of its magnitude. Let me put it like this, in terms of its magnitude. Okay, that means omega 2 is greater than omega 1. But because omega 1 was counterclockwise, means omega 1 was positive, and omega 2 is longer, that means, it's still counterclockwise. That means omega 1 is positive, omega 2 is positive, and omega 2 is greater than omega 1. That means when you do the difference between them, right, omega 2 minus omega 1, so let's say this is 5, and let's say this is 10, you can see, right, then you can do the difference, 10 minus 5, you get positive 5. Then you do the, ratio, delta omega over delta t, and you're going to get alpha. Okay. Well, it means that alpha, in this case, is going to be positive, right? So alpha is positive because you are moving counterclockwise and you're speeding up counterclockwise. Okay. That means your speed increases as you're moving in a positive direction. Okay. So one other example I can give you here is this. I don't have it in the slides, but let's imagine that you're given this, right? So you're given that, but let's say this omega 2 is actually a little bit shorter. Let's ignore this one. Let's say omega 2 is a little bit shorter. Okay. So let's say shorter means that its magnitude is less. So let's say it's 2. Omega is 2 radians per second. Well, what does it mean then? Well, if I do change in omega, I'm going to get omega 2 minus omega 1. You can see, right, it's going to be 2 minus 5 is going to be negative 3 radians per second. All right, so let's say then if I divide that by time, and let's say it's 1 second time, right? Let's say the time is 1 second, then it's going to be negative 3 radians per second square for the alpha. Well, look at alpha. Alpha is negative. Why alpha is negative? Well, because you are moving in a positive direction, but slowing down. Remember, this is just very similar to the, the linear case, right? Remember, if you're moving to the right and you're slowing down, your acceleration had to be in opposite direction. Well, same thing here. Moving in a positive direction, slowing down, acceleration then has to be negative. And you can then use this analogy, right? So to understand what will be the, let's say, angular acceleration, angular velocity relationship, if let's say this wheel is rotating clockwise. So if it's going, for example, if it's clockwise omega 1 and clockwise omega 2, that means, let's say the system is rotating clockwise at T1 and at T2. Well, that means you have negative velocity negative omega 1, negative omega 2, well, but you're speeding up in that direction, that means your alpha is also negative because you're still increasing your speed in that negative direction. That means you have an acceleration vector or alpha, which is also negative. But if you had, for example, if the omega 2 was less than, so for example, all right, let me do it here. So let's say this is omega 1. Let's say this is omega 2. You can see it's less. That means then alpha will be positive, because if you have a negative omega, but you're slowing down, alpha had to be in the opposite direction, which means it had to be then in a positive direction, right? So those are the things you guys have to kind of remember when you're dealing with, rotating system. Remember, this is very similar to the linear system, and we talked about that in, I think, chapter 2. It's been a long time, right? But we covered this. Maybe you can go look at some of the lecture notes from chapter 2. All right. So now, if you remember, as soon as we discovered that we can represent the linear motion in terms of displacement, velocity, and acceleration, then we decided that, okay, so then you can have two types of motion, right? You can have a linear uniform motion and linear non-uniform motion, okay? And when it was a linear uniform motion, I just gave you a few slides ago, right? I gave you the equation for linear uniform motion, and I gave you the equation for the linear angular motion, okay? But then a little more interesting, a little more realistic was, linear motion, non-linear motion, where objects speed up and slow down and changes direction and all those things. And that means we had non-linear motion. That means non-uniform motion, non-uniform motion. So input like here, non-uniform motion. Okay, so non-uniform motion where there is an acceleration, there's a change in velocity and things like that. And we had to take into account all of those things, right? But one of the important, let's say, simplifications, or important, let's say, a case that we used was constant acceleration. Remember, this one says constant angular acceleration, one thing like this. So remember, in a uniform case, when we said acceleration is constant, then we could use those 4 kinematic equations, right? So remember, kinematic equations was this: V final equals V initial plus acceleration times time. Equation 2, delta x was equals to V initial times time plus 1/2 acceleration times time squared. Equation 3, V final square equals V initial square plus 2 times acceleration times displacement. Equation 4 was in terms of displacement is equals to V initial plus V final divided by 2 times time. So we had those 4 equations to describe straight line motion, non-uniform motion, right, with constant linear acceleration. Okay, that means this was the key, that acceleration was constant, and we could use this constant acceleration, constraint, and use those 4 kinematic equations to describe any type of kinematic problem. What is the final position? What is the final velocity? What is the acceleration? How long did it take to go from A to B, and all of those things. Now the same thing we can do for the angular system. If you have an object, right, where we consider a particle, right? So for example, at some point P, and it's rotating 5 seconds, we can figure out how long did it take for it to get 1 cycle, 2 cycles, and what is the angular speed at a later time, and all those things. That means we can still have non-uniform angular motion. And if alpha is constant, that means angular acceleration is constant, then we can have kinematic or angular kinematic equations. Okay, so what are the angular kinematic equations? Well, it's the same equations as the linear kinematics. It's just everything linear replaced with everything angular. Look at the linear equation 1. V final equals V initial plus AT. Well, in the angular, system variables, V final is basically omega final. V initial is omega initial. A acceleration is alpha. Then times time. That means there's an angular variable for position, velocity, and acceleration. Obviously, time remains time as always, right? But kinematic equations are the same format. It's just you replace everything linear with everything angular, pretty much. Here's equation 2. Linear displacement, well, it's angular displacement, equals angular velocity initial times time plus 1/2, alpha then t squared. Equation 3, omega final square equals omega initial square plus 2 times alpha times delta theta. Equation 4, delta theta equals omega initial plus omega final divided by 2 times time. Okay, so as you can see, equations basically exactly the same format. Okay, that means all you need to know here is alpha constant or not? So if alpha, which is angular acceleration, constant, then you can use those 4 equations. Okay, and you can use what, let's say, why if it was not constant, let's say, or let's say, what if alpha was 0? Remember, this is uniform motion, and I gave you one equation, and it was delta theta equals omega times time. That's it. This is a special case where alpha is 0. You have just, that particular equation. Because one of the things you can do here is this. Even looking at these 4 equations, right? So when alpha is 0, means your angular velocity doesn't change. Okay? So for example, you can see in terms of this. So if you have, alpha 0, then this is 0. That means omega initial and omega final are the same. Well, if alpha is 0, this is 0, and delta theta equals omega naught times t, which is exactly what I have over there. When, again, alpha is 0, omega final is same as omega initial. And when, here this equation tells you that omega initial plus omega final over 2, but since omega final and omega initial are the same, their average is the same as their, same quantity as, any of the values. So again, you come up with the same equation. That means, you have uniform and non-uniform, and sometimes you have to decide if the problem is uniform or non-uniform motion. All right, so let's solve some problems and see how we can apply these kinematic equations there. Okay. We have a wheel rotates with a constant angular acceleration of 3.5 radians per second square. All right, so again, so you can't confuse this, right? So there's a constant angular acceleration of 3.5 radians per second square. That means it's a non-linear, non-uniform, motion with constant angular acceleration. That means I can use all the kinematic equations here. All right, so let's see. If the angular speed of the wheel is 2 radians per second at t equals 0, through what angular displacement does the wheel rotate in 2 seconds? All right, so let's do this one first. Okay, so then here's what I have. Same organization that we use for the linear kinematics, we can use it here. You write down what is given to you. Okay, so let's see what's given to me. I'm given that alpha is 3.5 radians per second square. And I'm given that omega initial is 2 radians per second when t equals 0, right? That means that's my initial. And if I'm given those two together, right, omega initial and alpha, and I want to know then I want to find, right, what is delta theta 2 seconds later when, let's say, t final here is 2 seconds. That means my time, delta t, right, time interval is 2 seconds. All right. So alpha, omega initial, and t is given, and I want to find delta theta. You go back to the kinematic equation, and you should be able to see that equation 2 will give you this. delta theta equals omega initial times time plus 1/2 delta t squared. Okay, so we plug in 2 radians per second times 2 seconds plus 1/2, 3.5 radians per second squared times 2 seconds squared. Okay, then you find delta theta, and this will be 11 radians. So you can leave it like this, the answer, right? 11 radians if you want. So let's say I will be more than satisfied with this answer. But sometimes it might be asking you to represent displacement in degrees. Let's say, what if it asks you to do that? Well, then you use one of those conversions, right? Where 180 degrees is pi radians. Multiply them, then you will get 630 degrees, which, let's say, if 11 radians is not very intuitive, well, 630 will be, right? Because let's say every rotation, every one cycle rotation is 360. And this is like, let's say, almost 2 cycles, right? So 360 times 2 would give you, let's say, 720, and this is 630. So maybe like a 1 full cycle and, 3/4 of another cycle. So let's say this is kind of like another way of representing that. All right, so let's see then for part B. It says, through how many revolutions has the wheel turned during this time interval? Well, remember, revolutions just means, how many cycles, okay? Now, the conversion for that is relatively simple, because one of the things we have here is that one revolution is just one cycle, which is it's equivalent to 2 pi radians, because that's the cycle displacement in radians, or 360 degrees, which is in terms of the degree. That means you can use either 11 radians or 630. So let's say if you take 630 degrees, where then 360 degree is one revolution, then you can use this to get that you're going to get 1.75 revolution. Okay, so you can represent that in terms of revolutions. Okay, so that means sometimes when you see, for example, this has nothing to do with this problem. For let's say you're given something as 80 RPM. Well, RPM is revolutions per minute. That means tells you that system undergoes 80 revolutions, 80 cycles in 1 minute. So RPM is revolutions per minute. That means you always need to convert this to radians per second before doing any type of calculations. All right, so let's look at then part C, which tells you what is the angular speed of the wheel at t equals 2 seconds. All right, that means, again, we're given angular acceleration, initial angular velocity, time. Now we found the displacement. The question is, what is omega final? Again, go back, look at those angular kinematic equations, and you will see that equation 1 is by far the easiest one to get final angular speed, because I'm given everything. So it's 2 radians per second plus 3.5 radians per second square times 2 seconds. All right. Omega final is 9 radians per second after we calculate it. Okay. Because this gives you 7 plus 2, you get 9 radians per second. All right, so you can see, right? It's very similar to the linear kinematic equations, right? So linear kinematic way of solving problems. So that's why it should be at least, I'm hoping a little bit easy transition for you guys to go from linear kinematics to angular kinematics, because as long as you identify everything the same way correctly, you have the table and everything, right? You just, pretty much same idea, same, let's say, format, right? Same approach to this type of problems. All right, so let's look at another one here. Okay. You have finished watching a movie on a Blu-ray and the disc is slowing to stop. Okay. Disk's angular velocity at t equals 0 is 27.5 radians per second, and its angular acceleration is a constant -10 radians per second square. So a line PQ on this disk, on the disk surface, lies along the positive x-axis at t equals 0. All right. So what is the disk's angular velocity at t equals 0.3 seconds, And what angle does the line PQ make with positive x-axis at this time? This time, which means like when time equals 3.3 seconds. All right. So let's see what's given to us. All right, so let's say you can see that you are given omega initial, which is 27.5 radians per second. And you know, right, you know that it's slowing down. That means if you have a positive velocity and you are slowing down, that means your acceleration has to be negative, remember, right? So that's why alpha is given as negative 10 radians per second square. But here's the thing, sometimes it might not even be given to you as negative. You might be told that angular acceleration's magnitude is 10 radians per second. But because it is slowing, you have to understand that you have to put negative always, even if it doesn't specifically tell, give you or tell you. All right, so that means we can also say that theta initial here is 0 because we are initially at the positive x-axis. Okay, and then time equals, so time is equals to 0.3 seconds. All right, so find omega final. All right, so again, omega initial, alpha, time, those three things given to you. How do we find omega final? Well, those two with the time is good enough for me to use equation 1, where omega final equals omega initial plus alpha times t. Okay, and this is equals to 27 radians per second, then minus 10 times 0.3 seconds. Then I'm going to find omega final to be 24.5 radians per second, which makes sense because, if you're slowing, any later time, you're going to be having less, magnitude speed. So smaller, smaller speed. All right, so that's omega final. So that's for part A. Part B is asking what angle does the line PQ with positive, what line does it make with the positive x-axis? All right, that means we want to find displacement. Okay. Now, at this point, you can either use equation 2, delta theta equals omega initial times time plus 1/2 alpha t squared. You can easily use this equation to solve for delta theta. Now, you can use this equation to solve for delta theta because you have everything else, right? Again, and you can use this equation to solve for delta theta. And you choose which one you want to use. Either one of them will give you the right answer. I have in my slides, the lecture notes, I'm using, this, equation 2. Well, I can also use equation 3 or equation 4. And if I would do that, let's say I would use equation 4, for example, because it's going to be 27.5. Well, here I should use 27.5 plus 24.5 divided by 2 times 0.3 seconds. Whichever equation you use, you should get the same answer. So here I'm going to get, for example, 7.8 radians. And if I use this, conversion factor where, a 2 pi radian, technically I'm done with this. I can go further, maybe because asking what angle, right? I can go further and represent even with the revolution. So 2 pi radian is 1 revolution, and we can get 1.24 revolution. But let's say this is optional. This is an extra information that you can give me. Information in theta as an angular displacement would have been good enough for me. Okay. All right, so let's continue. So next we're gonna kind of bring those two types of motion, linear and angular motions together for a rigid object. Okay. So imagine you have an object, like it could be some kind of unusual shape like this. You can see some kind of unusual shape. But this object here is fixed at the center, right at point A. That means it is going around with respect to that point A. So that we call that axis of rotation. So that's our axis of rotation. So that point is our axis of rotation. That means the entire system, right? Entire rigid object rotating with respect to that point. Okay, that means everything is rotating but that point. Generally, we can say that axis of rotation is the only point in your system that is not rotating, because everything is rotating with respect to that point. But at the same time, every single particle in that object, right? Every single particle in the rotating object is moving around, right? Moving around. So for example, what I can say here is this. So look at this point P, okay? That point P has same angular, let's say motion as any of the other point in that object, right? That means, see if this particle undergoes this, rotation, right? For, let's say full cycle rotation. At the same time, if I would have chosen something over here, that object will undergo circular motion. Something over here, that will undergo circular motion, okay? That means every particle has the same delta theta and the same omega exactly at the same time. That means they all undergo same displacement at the same angular speed. Okay, so that's why every point undergoes the same angular motion. But how about the linear motion? So how about the linear motion? So that's different. That's different. Again, so let's say if I take 2 points, right? One is here. So you can see, right? This one has let's call this R2, and this one is R1. So you have 2 points. Let's say P1, P2. Okay. Imagine this object is rotating. That means this is the displacement of that point 2. This is the displacement of that point 1. And as the disk is rotating, right? As the disk is rotating, then one thing I can say is this. Delta theta of 1, which is angular displacement of 1, and I want to compare that to the delta theta of 2, angular displacement of 2. Well, one thing you can see here is that this is the displacement for this, point 2 in one cycle. This is the displacement of point 1 in one cycle. Well, right, so something like that, right? Well, are they the same or are they different? Well, remember, what is the angular displacement for one cycle is 2 pi. Well, point 2 goes 2 pi, point 1 goes 2 pi. That means delta theta 1 is equal to delta theta 2. Those two particles have the same angular motion, same angular displacement. Well, how about, let's say we measure time. So delta T1, delta T2, and let's say we divide their displacement with the time. Well, does it take the same time for point 1 and point 2 to undergo same displacement? Yes. Delta T1 always the same for any particles inside that, object. That means I have the left side, delta theta 1 over delta T1, and that gives me omega 1, which is the speed of the particle 1. This will give me then the speed of particle 2. And because delta theta 1 is same as delta theta 2, delta T1 is same as delta T2, then you can say that omega 1 and omega 2 are the same as well. That means they have the same angular displacement, same angular motion, that means same angular velocity and everything like that. Okay. But how about the linear motion? Okay. Remember, for the linear motion, I'm not looking at the delta theta. For the linear motion, I'm looking at, arc length, delta S1, and comparing that to delta S2. That means what I have here is, let me, maybe choose different colors so it will be easier. So for the angular, right now the linear displacement, I'm comparing arc length. That means things like this. So this is the particle 1. That means all that distance, right? So this is the distance of the particle 1 undergoes. and compared to the distance that particle 2 undergoes. All right, so what is delta S1? Delta S1 is 2 pi R1. Delta S2, 2 pi R2. Well, which one is bigger or which one is smaller? Are they the same? Well, one thing you can see here is, remember, this is circumference, right? So circumference of particle 1, hopefully you guys can see, is bigger than circumference of particle 2. That means this is bigger. You can see, right, where delta theta 1 was the same as delta theta 2 because both undergo same 2 pi radian displacement. Well, linear displacement is not the same for, 0.1, 0.2, because the circumference that 0.1 and 0.2, right, they have different circumference because 0.1 is further away from the axis of rotation, so it has to cover much bigger distance. It has a much greater circumference. Well, then how about if I divide delta S over time? Remember, if I take the delta S divided by delta T, what I get here is V1, and here I will get V2. That means velocity of particle 1 compared to velocity of particle 2. Well, but because the particle 1 has a much greater displacement, well, it has much greater, speed or velocity compared to 1. That means you can say V1 is greater than V2. Particle 1 is moving faster than particle 2. That means any particle that is further away from the axis of rotation, that means further you are, faster you have to be moving, because the time it takes for particle 1 to go around is exactly the same as particle 2 to go around. It means time is the same, but particle 1 has a bigger distance than particle 2, so it has to be, see, it has to cover bigger distance in order to get to the same, let's say, position, right, or complete one same cycle during the same time, so it has to be going faster, okay? That means we can think of, like, let's say, this velocity of particle 1 and particle 2 as the object goes in a circular motion, right, is not the same. Omega 1, omega 2 is the same. V1 and V2 are not the same. So that's why, would you rather work with a system where every particle has the same angular velocity, or the system where every particle has different linear velocities? It's the same, right? But linear velocity, if I'm using linear velocity, I have to keep track of every velocity because they're all different. If I'm using the angular variables, I don't have to do that. Every single particle have the same angular velocity. They have the same angular displacement. Say they have the same angular acceleration. But that's not true if you are talking about linear variables. So that's why. So point P in the figure moves in a circle. So this V here is, we're going to start calling them tangential velocity. So this is the tangential velocity. And you can see, right, it's because it's tangent to that circle. Okay, basically the trajectory. So it is called a tangential velocity. Okay. And one of the things as we said, right, so here's V1, here's V2, and they're not the same. And they're not the same because they have different distance from the axis of rotation. So that's why one of the things I can say here is, when I'm looking at, let's say the magnitude of the tangential speed, I have to, take into account how far away that point is from the axis of rotation as well. Okay, so remember, one thing we have here is, so let's say this S equals R times theta, exactly what I used to describe all of this right now. So if I'm using this equation, right, so S equals R times theta. So if I use delta S equals R times delta theta, that means I'm looking at the displacement. But here's the thing, if I then measure the time as well, I'm going to take left side divided by time. I'm going to take right side divided by time. That means divide both sides by time. So the left side, what I have here is delta S over delta T. That quantity gives me speed, and linear speed, or linear velocity if you want. On the right side, I have R, which is the distance of that particle relative to the axis of rotation, then times delta theta over delta T. That means R times ratio of angular displacement over time, and that's omega. That means this is my equation. V, linear velocity, equals angular velocity of the particle times how far away the particle is from the axis of rotation. So that's why it is position dependent. So it is depending how far away the particle in that object, right? How far away it is, with respect to the axis of rotation. Closer you are, slower you're moving. Further you are, faster you're moving. That's kind of like what we have to do, because further you are, bigger your, linear displacement. That means more distance you have to cover, so you have to be moving faster. All right, so again, this is the equation that relates linear velocity and angular velocity, just like how this equation relates linear displacement to angular displacement. That means we have two equations that relate linear and angular variables. Again, linear velocity, angular velocity, and you go from linear to angular by multiplying angular by r. Same thing is here. This is linear, this is angular displacement this time, right? And you can calculate the linear by taking the angular and multiplying by the distance. So kind of like same format, right? All right, so same way we can talk about then acceleration, because remember, one of the things we have here is if there's a change in speed, right, or change in velocity, there's acceleration. But also this particle, right, well, it undergoes circular motion. That means there has to be radial or centripetal acceleration. And you have now possibility of two types of linear acceleration. One, we call tangential acceleration. So this tangential acceleration is equals to r times angular acceleration. That means the tangential acceleration is the position of the object times the system's angular acceleration. So you can think of like this one is responsible for changing speed. Whenever your object changes speed, then you can say that there is a tangential acceleration. So your system has tangential acceleration. Okay, but remember, you can also go around in a circle with with no acceleration, right? Either angular, no angular acceleration. So remember, we call that uniform angular motion. So if there's a uniform angular motion and alpha is 0, then how can you then go around in a circle? Remember, you need centripetal acceleration to go around in a circle. Well, in a way, what we have here is there is always a centripetal acceleration, because when you're considering an object going around in a circle, let's say, a rigid object going, rotating with respect to some axis of rotation, there's always, centripetal acceleration for any point in that object. Remember, centripetal acceleration equation was speed of the object squared divided by the radius. Well, not necessarily radius, or position of the object or distance of the object from the axis of rotation. Now, this will work even if there is no acceleration. All you need here is either a speed, right? So how fast it is moving at that instant. If it is moving at 3 meters per second, then you can calculate acceleration. Even if it continues always moving at 3 meters per second, that means it never changes its speed, you still have a centripetal acceleration. All right, so now this equation here is we're deriving the equation on the left side. It means what we do here is this. So remember, it's speed square divided by radius. Well, remember, speed, linear speed is equals to r times angular speed. Now, one of the things I can do here is I can say, okay, so it's speed square, so it becomes r omega square, replacing speed with r times omega, then divide by r. So this becomes r square omega square divided by r, and I can cancel this r and r square, and then we end up with that equation. So you can see whatever is left is that equation. That means you have two equations for the centripetal acceleration. One you can calculate in terms of, linear speed. The other one is in terms of, angular speed. That means you're going to get the same answer. You just, depending which one you want to use. All right, so tangential acceleration changes speed. Centripetal acceleration, then remember, is changes direction. Okay, that means you have always centripetal acceleration, but under some conditions, you might also have tangential acceleration. That means if you have both, you're gonna, this object gonna go around in a circle and it's gonna start speeding up. So speeding faster, 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 right? Or start slowing down. That means whenever there is a speeding up or slowing down for the object, that means you also have a tangential acceleration. That means you can calculate the total acceleration. Remember, what we have here is then tangential acceleration and centripetal accelerations basically become the components, right? So you can say, right, so the acceleration as a total vector equals its centripetal component plus its tangential component. So this one changes your speed, centripetal changes your direction, tangential changes your speed. And if you have both, that means you change your direction and speed exactly same time. If you have only centripetal, you're going around in a circle at constant speed. If you have just tangential, you're going in a straight line and changing speed. If you have both, right, then you can do both. And you can calculate the acceleration, total acceleration magnitude by taking the square root of tangential square plus radial or centripetal square. Why? Because remember, the tangential and radial or centripetal are the components of the total acceleration. So you can find the magnitude and even the direction for this one, right? So let's say in this case, radial over tangential, you can even do that. All right, so you can do that to find, let's say, what is this angle theta here for the acceleration vector. All right. So again, we kind of talked about all of those linear quantities, right? Linear displacement, linear velocity, linear acceleration. And now we hopefully more comfortable with angular velocity, angular displacement, angular acceleration. And we can kind of like put everything together, right? Because you can represent the motion of the object, even rotating object, right? Completely with linear variables. That means delta S, V, and A. You can use those three. But the problem here is that if you're using linear variables, every particle has different linear variables. That means every particle has a different linear displacement, different linear velocity, different linear acceleration, right? Because you could see from the equation, delta S is equals to R times delta theta. So it depends on position. V is equals to R times omega. It depends on position. Let's say AT equals R times alpha. It depends on position. That means if you're considering a rigid object, then every particle in that rigid object is going to have different linear variables. But that is not the case if you're considering angular variables, okay? So you can say, right, all objects on the rigid object will have the same angular speed, but not same tangential speed. That's right, because see, the tangential speed equals angular speed times position of the object. If you have 2, 3 objects, different position with respect to the axis of rotation, they have different tangential speed. Okay. All points on the rigid object will have the same angular acceleration, but not the same tangential acceleration. Again, alpha is the same for all, but tangential is not because it's position times the alpha. So if you have different position, you have different alpha, different A. So that's kind of, you can say, right, AT is equals to R times alpha. If you have 2 particles, one has a greater distance, it has a greater tangential acceleration. Pretty much simple as that. All right. So the tangential quantities depend on R, and R is not the same for all points on the object. Again, last time, let's think like this. So you have, here's point 1, and maybe here's point 2. See, point 1 and point 2, when they undergo one full cycle, they're going to have the same delta theta, they're going to have same delta omega, they're going to have same alpha. Let's say, let's say same alpha. But see, this is the tangential velocity of 1, this is tangential velocity of 2. Because one of the things we have here is 1 and 2 have different distances. That means V1 is going to be less than V2. Delta S1 is going to be less than delta S2. and AT1 is going to be less than AT2. That means you have two different already particles, and they all have different linear variables, but they all have the same angular variables. That's why we're always going to prefer using angular variables if you're talking about a rotating object. All right. Another important thing we can, measure or calculate about the rotating object is the energy associated with the object. Remember, it's a still object rotating. That means if I consider, let's say, one particle in that rotating object, well, it has a speed. It is moving around in some speed. That means I can calculate kinetic energy. Okay. All right. So then kinetic energy that I am considering here is, for example, 1/2 m times mass of the particle times speed squared. Okay, so let's say this is initial kinetic energy, so 1/2 mi/vi squared. Okay, well, here's the thing. One of the things I have here is it's a rigid object. It's not just one particle. Okay, that means this is just one of many particles. That means there's another one right here, another one right there, thing like this. So then this one going to be moving in this kind of path. So this one going to be moving in this type of path, right? So then what we do here is, let's say we say, okay, so here's K1, 1/2 mass 1 V1 square. Here's K2, 1/2 mass 2 V2 square, and so on and so forth, right? And add every single one of them in an equation, okay? So you can see, right? One of the things you get here is this. So let's say if you're calculating total kinetic energy, so let's say it's K1 plus K2 plus K3 plus Ki, right? And what you have here is this, 1/2 m1 v1 square plus 1/2 m2 v2 square, and what you have is that they all have same, 1/2, right? And but what you have here is, so let's say you can factor out 1/2, but what you have here is that you have this m1 v1 square plus m2 v2 square, and so on and so forth. Okay, so but here's what we do in this case. Okay, so I'm gonna do it here so you guys can see the derivation. So again, I have this K total is equals to then 1/2. Then here what I have is this m1 v1 square plus m2 v2 square plus right, for all of them. But instead of using linear speed, what I'm going to do here is I'm going to replace linear speed inside the parentheses, right, with the angular speed. Remember, I can do that because linear speed is equals to position r times angular speed, right? I'm using this equation that relates linear and angular speed. So that means for V1, so think like this, V1 is equals to R1, position of particle 1, times its angular speed, 1 squared, plus M2 angular and, V2 square, I'm replacing with R2 angular speed 2 square, plus . All right, so what do we get here? So I get this 1/2, then I get M1 R1 omega 1 square plus M2, square, R is also squared. So M2 R square omega 2 square plus M3 R3 omega 3 square, plus all of those. But here's the thing. We just said that angular speed for particle 1 is the same as angular speed for particle 2, same as angular speed for particle 3, and so on and so forth. That means this angular speed, right, for those particles is the same. That means one of the things I can do here is I can drop the subscript for omegas because they are the same for every single particle. Well, if they are the same, then I can remove that from the parentheses. And what I get here is this, 1/2, then M1 R1 square plus M2 R2 square plus M3 R3 square plus and I remove omega square because that omega square is constant for all of them, so I can remove from the parentheses. All right, so now what we end up here is this. So you are looking at an equation where you have 1/2 here, omega square over there, but inside you have this quantity. So this is for the particle 1. So this is for the particle 1. Mass of the particle 1 times its position squared. And here's for particle 2. Mass times position squared. And here, mass times position of the 3 squared, right? That means what we're doing here is we're basically summing up the mass and position square for all of those particles, right? That means I can just represent it like this, right? So in terms of sum of the I number of particles, right? Where I'm I'm adding their product of mass and position squared. And this is an omega square. Okay. That means in the parentheses, I have sum of all of their mass times position square quantities. Okay. Now then, one of the things we do here is that quantity, right? That quantity is very important in the rotational system. Okay. All right. So hopefully you guys were able to follow the derivation. Remember, you can just rewind and watch it again. So let me kind of get rid of this, so then we can continue with some of the more info on the slide. All right. Better. All right, so then what I can do here is this. So again, so you can see, right, then total kinetic energy, as I derived it, right? So it's 1/2 times whatever I have here in the parentheses, sum of the mass times position squared for every particle, and times the constant omega square, right? So now, that quantity inside the parentheses is known as moment of inertia, because that quantity is equivalent to the moment of inertia for the linear system as well. So remember, so far we talked about this, right? There's an equivalent for delta x or delta s. Remember, this is the same, right? Delta s is the same as delta x or delta y, linear displacement. So we have equivalent for this one here. And then we had v. Well, we had the equivalent of that one here as well. We have a. Well, we have equivalent for that as well in the angular system. But then we also have the mass. Well, we have equivalent of that as well, and that is known as moment of inertia. And we are then defining that that sum in the parentheses, and we give it like, I, right? So we say that that's the moment of inertia of the object of the system. Okay, so the rigid object. And basically this is kind of equivalent. That means the moment of inertia is kind of like mass equivalent. Remember, when you're trying to move the object, the mass was kind of like the inertial factor, right? So let's say heavy objects are not going to be, very easily moved around. Or, light objects, have no problem, just push it a little bit and it just moves. Where you can think of, like, let's say here, moment of inertia gives us, a way of figuring out if it's going to be easy to rotate the system or not. Okay, so you can say the moment of inertia is a measure of an object's resistance to change in its angular speed. The moment of inertia depends now not only on the mass of the rigid object, but also on how the mass is distributed around the rotation axis. And that's the very important thing. To make the object rotate, we not only need to know about its mass, but also how the mass is distributed. Okay, because for example, if you are trying to rotate a meter stick, okay, so and let's say the meter stick is 5 kilograms. Okay, well, meter stick, and let's say I want to rotate with respect to center. Okay, with respect to center, and what I'm looking at here is, okay, so the total mass is 5 kilograms, and let's say the mass is distributed uniformly everywhere. That means then if I want to rotate with respect to the center, right, I probably will have, no problem rotating with respect to its center. Okay, I have no problem with respect to, because left and right sides have equivalent mass, and the rotation going to be, pretty straightforward. But let's say you have the same amount of mass. That means you have another object, 5 kilogram, but this is, let's say, I don't know, a baseball bat, like this. Okay. So now, will I have the same, easy time rotating this object with respect to the center? And obviously it's not, because left side is heavier than the right side, because the mass is not distributed evenly. That means the moment of inertia of this guy will be different. Also, one of the things I can say is that, if I'm rotating either one of them with respect to the, let's say, the edge, is it different from trying to rotate with respect to the center? The answer is, again, yes, because it's completely, because one of the things you have here, you have different distribution of mass, with respect to the axis of rotation. So again, you're going to get different, let's say, rotating resistance from that moment of inertia. Okay, so we'll still talk about that a little bit later on, but think like this. So this is kind of equivalent to, mass in our, linear system. Heavier object is harder to, move or change their motion, right? Same thing is here, like in terms of if the object has high moment of inertia, it's going to be harder for us to, rotate that. Where, one thing you can see here, right? Moment of inertia increases with mass, also increases with the position of the particles in that object, squared, right? That means, see, if it's a point particle, it's basically mass times position square, okay? That's why not only how much the particle has mass, but also how the, distribution of the particle is, that also plays a role. Okay, now then the total, not the total, or total rotational kinetic energy. So again, if I'm replacing the parentheses with this moment of inertia I, so it becomes 1/2 I omega squared, where again, I is the moment of inertia, omega is the angular speed. That means rotational kinetic energy becomes that. Okay, so again, rotational kinetic energy is not a new type of energy. The form is different because it's applied to the rotating system. In a way, you can think like this. So this is your total kinetic energy. So you can have a rotational, or you can have what we call linear, right? So let me put like linear now, but we're going to be calling translational later on. But this is kind of what you have. That means you have, let's say, 1/2 I omega square if it's rotating. But if it's rotating and moving at the same, like let's say I don't know, soccer ball, right? It's rotating, right? It's spinning on its axis, but also it's moving linearly. That means I can also calculate, like, let's say 1/2 mv squared. That means this is due to its rotation. This is due to its linear motion. So you can kind of combine those, two quantities together. All right. So then the unit is still joules because it's, it's still, kinetic energy. Okay. All right. So now, if then we consider a rolling motion of a rigid object, like a wheel, or let's say a disc or a ball or a sphere, right? When they're rolling, one of the things we can do here is we can see that different part of the, the object kind of have different, speed, like, let's say, for example, when you talk about the rolling, because when you talk about rolling, we're considering, let's say, combination. Okay, so like combination. So let me give you like an example for, so let's say here's the object that is moving linearly only. That means it's a object, right? But you're sliding it. It's not, it's on the surface, right? But think like this, you're sliding. That means there's absolutely no rotation. Well, when you're sliding, that means the center, so this is V center of mass, that means its center of mass is moving at the same speed as the top. Or at the bottom, right? That means, remember, so think like it's a object that you're sliding. So you're sliding, you're just moving linearly without rotating. That means the top, bottom, or the center, they're all moving with the same, same speed. All right, so this is, let's say, linear. Or you can have, object that is, same object, let's say, if you fix it at the center and start rotating, so this is rotating, then you can see, right, when it's rotating, let's say clockwise, then what we have is that the top moves with the center of mass speed. The center, well, the center has no speed, right? Because remember, the if you're rotating the center of, this, it becomes like here, it becomes axis of rotation, and well, axis of rotation is not moving at all. So V center of mass equals 0, right, over there. So this is, let's say, center of mass. At the bottom though, well, if it's rotating the bottom, then we'll be actually moving in this direction, right? So V center of mass speed, okay, because it's rotating clockwise. Well, rolling is a combination of those. That means you're combining linear and rotation. Well, if you combine, let's see what happens at the top. Well, top you have positive velocity plus another positive velocity. Well, top has 2 times, right? So let's say top is 2 VCM because you're adding, from linear and, rotating. That means for both, contribution, you have a, positive velocity, same direction, so you add them. Well, let's look at the center. From linear, it has VCM. From, rotational, it has 0. So the center is moving with just VCM, V center of mass, basically. How about the bottom? Well, bottom has positive plus negative. Well, a bottom has no velocity, which you can see from this picture, right? Top has 2 times center of mass, center has 1 times center of mass velocity, and bottom has 0. That's why a lot of times when we're considering the friction as something that propels you forward, we always consider static friction, because static friction, means that the bottom of this, rolling object, or the tire, or a ball, or whatever it is, the bottom instantaneously is at rest. Okay, so it's kind of counterintuitive, but that from the vector point of view, right, it works perfectly fine, because what you can see, right, you can see that we're considering at the bottom there is a positive velocity component the bottom has from a linear contribution, and negative from the rotational contribution, and they cancel each other. So that's why in order for you to roll, you need friction. If there is no friction in this object, in the slide, it's not going to be rolling. But if you're rolling, then you need friction. So that's why in that case, we can consider, object that when it's kind of going down an incline or something like that, in its friction in order to roll. Okay. So this is kind of like, let's say, let's kind of get rid of this. So the total kinetic energy of a rolling object is the sum of the translational energy of its center of mass and the rotational kinetic energy about its center of mass. As I said, right, so this is total kinetic energy, which is, this is a rotational kinetic energy plus, so we call this translational. So translational, so I'm not going to use linear anymore. So this is translational kinetic energy, which is mass of the object times its center of mass speed squared, where the rotational is moment of inertia of the object times its angular speed squared. All right, so here's then what I have. So we're going to look at an example. Okay. By the way, this is says for an arbitrary axis, the parallel axis theorem often simplifies calculation. So there's, for example, one of the things we're going to see. This will, this will help you when we get to the. Okay, so things like this. I'll come back to this one. I'll come back to this slide, in a little bit. Okay. So here's what we have. You can see, right? I'm going to consider, for example, an object going down an incline. So here's an object going down an incline. Remember, before we consider this, for the conservation of energy, right? Conservation of mechanical energy, you need to have no friction. It has to be frictionless surface. Okay. An object, let's say a box, right? We'll slide it down. So then you have, let's say, kinetic energy at the top plus potential energy at the top equals kinetic energy at the bottom plus potential energy at the bottom. Okay. And you can have a conservation of mechanical energy. Okay. But if object here instead of box is some kind of, a disc or a sphere, right? There is going to be a rolling. Well, you need a friction. You need friction. And you can see right here is, despite the friction, no loss of mechanical energy occurs because the contact point is at rest relative to the surface at any instant. That means, can I still use this equation, like conservation of mechanical energy, even if there is a friction? Yes, if your object is rolling. You can still have object, in terms of its kinetic energy, right? Just, in terms of kinetic energy and potential energy, and there is no loss of energy at point 1 and point 2. The only difference here is this. You have not only, you have not only a rotational kinetic energy, not only translational, but also rotational, okay? That means your kinetic energy is equals to 1/2 mass of the object times its speed square. This is linear, right? Contribution. Then plus 1/2 I omega square. And this is its rotational contribution. Because if the object is rolling, well, you need to have those both, okay? One of the things we're going to see then is whenever you're considering, let's say, what if I'm asking, so what is the speed 2 at the bottom? Okay, what is the speed 2 at the bottom? Well, you can solve this problem by, let's say, what I mean by speed 2, but let's say speed of the center of mass. When I say speed, is the speed of the center of mass. So here you have a speed over there, okay? But then what do you do with this term, second term? Well, what we do here is this. We use where omega, right? So omega is equals to V over R. Remember that equation where V is equals to R times omega? So then omega equals V over R, okay? That means I replace omega with V over R in this, rotational kinetic energy equation. That means what I'm gonna end up here is this. So 1/2 mv squared plus then 1/2 I, and then here I'm saying that's V over R square, okay? This is one of the things that you will be, doing whenever you are calculating, because see now, same V over there as over here. So both terms now have the same speed, okay? The same linear speed. That means when I'm calculating the speed, just basically take that V, right? And it's V squared, both, in both quantity, let's say for both of those, right? So I just factor out and then solve for that. When I leave it in terms of omega, it's kind of confusing. I need speed, but there's omega. Well, again, all you do is just replace omega with V over R. That means if I go back over there in that equation, and I want to find, let's say, what is the speed of this, of that rolling object at the bottom? Well, what I have to do here is this. So kinetic energy 1 plus potential energy at 1 equals kinetic energy 2 plus potential energy at 2. So hopefully from the previous, chapter 7, you remember that if I take then the ground to be my reference position, then there will be no potential energy over there. And for example, what I do here is I take my point 1, which is at the top, is when I start from rest. There's also no kinetic energy over there. And then let's say what I get here is then the potential energy at the top, let's say mgy1, is then equal to the kinetic energy at the bottom, K2. But now K2 is written as 1/2 mv2 square plus 1/2 I omega square. Okay, like let's say omega 2 square, because but what I have here is this then. By the way, remember, so if the speed 1 is 0, so is omega 1 is 0, right? Because speed and omega are related to 1. So if this is 0, you can see, right? V is 0, omega is 0. So that's why kinetic energy 1 is 0, both translational and rotational if object starts from rest. All right, so, and then what we do here is this, right? So we have mgy1 equals, so then I have 1/2 mv2 square plus 1/2, and again, I rearrange this using the omega equals V over R, so it becomes I V square over R square, right? If I put that and just, calculate. And then from here, you have then this equation. There are a number of things you can do from here, right? So let's say, you can go ahead and calculate, let's say, for the, speed 2, right? So just rearrange, factor out speed 2, right? So then let's say speed square is going to be equals to mgy1 divide, so 2 times mgy1 divided by, 1 plus moment of inertia, right? So you guys can, see that, it end up being something like that. So again, but one of the things I want to always say is that just, let's say, take this equation over here, because this equation can now allow you to solve, let's say, a number of things. And if you want to solve for V2, just rearrange it and solve for that. Okay. I have an example which you guys will see then, how do I do that? All right, so then one question here is this: how do we then find this moment of inertia quantity? Okay, so about 90%, 95% of the time, that moment of inertia is already kind of calculated for you or given to you, equation. Because the object that we're going to be using a lot of times has a, good symmetry, like symmetrical, let's say, objects. It could be like a sphere, it could be a disk, it could be a, a rod, or a shell, right? And moment of inertia for all of those things are given in this table. Okay, so for example, if you have a hoop or a thin cylindrical shell and it's rotating with respect to its center, then you can say, right, moment of inertia of the entire thing with respect to the rotation of center of mass, which is the center, right, is equal to the mass of it times its radius square. So here's radius, here's its mass times radius square. That means total mass times radius square. Well, what if you have a solid cylinder or disk? So this is usually work for pulleys. Okay, so the pulley have, like, let's say, a size, right, a radius, and what you can do here is you can then represent the 1/2 times mass times radius square. Okay, so the pulleys then can be always assumed to be a disk, solid disk, and it's center, and if it's rotating with respect to center of mass, then moment of inertia with respect to center of mass of the disk, right, or the pulley, is always going to be, 1/2 times the mass of the pulley or the disk times its radius square. Okay, that means you can see, right, you can still take that moment of inertia and present it in terms of, mass and radius. Okay, then you can have, let's say, a rod. So you see a rod, it's a uniformly distributed rod, but it has two different equations or two different, let's say, axes of rotation. One, you can rotate with respect to center. The other one is you can rotate with respect to one of the ends. And you can see, right, moment of inertia is 1/12 mass times length square if it's rotating through center, or 1/3 ml square if it's rotating at one of the ends. And obviously you can see, right, if it's rotating through center, it has a smaller moment of inertia, which means it's easier to rotate it than when it's rotating at the end. Larger the moment of inertia, harder it is for us to rotate the system. All right, and here's what I have. If you have an object that is going down and it's, let's say, a ball or a solid sphere, moment of inertia is 2/5 times its mass times its radius square. That means if you know it's a solid sphere, you use that moment of inertia. If you know if it's a thin spherical shell, you use 2/3 mr square, and so on and so forth. That means you read the problem, you identify the shape, and you use the moment of inertia from one of this, let's say, from this table, right? And just remember, the pulley is always, a disk, so it's 1/2 mr square. Any type of ball is basically a marble, a golf ball, whatever it is, right? So it's 2/5 mr square because it's a solid sphere. All right, so let's look at, this example over here. So we have a rigid rod of negligible mass lying along the y-axis, connect 3 particles. The system rotates about the x-axis with an angular speed of 2 radians per second. Right. Then find the moment of inertia about the x-axis. Okay, so find the moment of inertia of my system with respect to x-axis. And what I have here is this. So I have 3 masses, right? So you can see, right, here's 4 kilogram position y equals 3 meters. And I'm going to take this point O as my axis of rotation. That means what I want to know here is what are, let's say this guy here is my mass 1, right? So this is mass 1, okay? And let's say this is mass 2, and this is mass 3. That means this becomes my position 1. This becomes my position 2. This is position 3. And remember, moment of inertia is the sum of mass times position squared for every particle in my system. And if I have a point particle system like this, you can see, right, I have 3 objects because the rods, right, are negligible mass. So that means the rods doesn't contribute to the moment of inertia. That means this is just M1 R1 square plus M2 R2 square plus M3 R3 square. Okay. So M1 here is 4 kilograms times its position squared. Now position is relative to the center or the axis of rotation, which is in this case the center here, right? So this is my R1, and this is just a 3 meters from the axis of rotation, and you square that. Plus mass 2, and that's 2 kilograms times its position, and that's 2 meters, right? It's -2, but it's a position. But I want is just just how far away it is, and this is just 2 meters from that square. Then plus my mass 3, which is 3 kilograms times its position, and it has a position of 4 meters, right? It's 4 meters away from the axis of rotation, so I put 4 meters squared. Okay, that means what I can do here is just add them all together to find my moment of inertia of my system. Okay, and one of the things I can see here is if I add all of those together, I'm going to get 92 kilogram meter square. That means the units for the moment of inertia is kilograms times meter square. And that means my system has a moment of inertia of 92 kilogram meter square. All right, so part B, it says, what is then the total rotational kinetic energy? All right, so I can calculate total rotational kinetic energy by saying 1/2 moment of inertia times angular speed squared. And we were given that the system is rotating at 2 radians per second, angular speed. That means 1/2 times moment of inertia, which is 92 kilogram meter square, times then 2 radians per second, and we're going to calculate 184 joules. Okay, so that's the rotational kinetic energy. Okay, that's part B. Part C, it says, what is the tangential speed of each particle? All right, so now to calculate tangential speed, what I need to do is this. V1 equals R1 times omega 1, which is position of particle 1, which is 3 meters, times the speed, which is 2 radians per second. And that's going to give me 6 meters per second, right? Because it's meters times something per second. Remember, radian is not a real unit, so it's meter per second. All right, so I get 6 meters per second for V1. All right, so same way, V2, I can say it's 2 kilograms times 2 meters. I'm going to get 4 meters per second. And V3, which is 3 kilograms and 4 meters, I'm going to get 12 meters per second. Okay. Sorry. My bad, not mass. This is just a position 4 meters times angular speed, which is 2 meters per second. And that's 8 meters per second. All right. So those are my V1, V2, and V3. Part D says, then find the total kinetic energy by finding kinetic energy of each one and adding them together and calculating kinetic energy like that. Because what I did here for part B, I calculated kinetic energy from the system point of view. That means the system has 2 radians per second angular speed. The moment of inertia of the system is 92 kilogram meter square. and I use that equation for the system, and I calculate 184 joules. But I can also calculate by taking kinetic energy, finding kinetic energy of 1, adding it to the kinetic energy of 2, and kinetic energy of 3, and finding the total kinetic energy, which is just, 1/2 m1v1 square plus 1/2 m2v2 square plus 1/2 m3v3 square. Okay, but still, if you do that, what you will get here, you're going to get same thing, which is 184 joules. Because it doesn't matter if you take the linear approach, which is finding the speed, finding the kinetic energy of each one, and then adding them together, or using the angular approach, which is finding the angular speed and moment of inertia of the system, and using that, you're going to get same thing. And obviously, you can see, right, it's much easier to get the first approach, which is angular approach. Just find the moment of inertia and use the rotational kinetic energy from 1/2 times moment of inertia times angular speed square. All right, here's one other problem. So we have a couple of problems from the moment of inertia. Oops. So here we have a dancer spinning at 72 RPM about an axis through her center with her arms outstretched as shown. From biomedical measurements, the typical distribution of mass in a human body is as follows. Head about 7%. Basically, in terms of like the head has 7% of the mass. Arms 13% for both. Trunk and legs about 80%. All right. Suppose you are this dancer. Using this information plus length measurements on your own body, calculate your moment of inertia about your spin axis, which is, as you spin around center of your mass, right, center of your body, what will be your moment of inertia? And use the figures shown to model reasonable approximation for the pertinent parts of your body. Okay, so think like this. I'm going to use the values that I have in my, let's say in my slide, but obviously your values might be different. So one thing I used here is 90 kilograms, which is definitely not the mass of a dancer like that, okay? But still, let's say 90 kilograms. That means what I have here is, then the head will be, so mass of the head is then 7%. That means 0.07 times this 90 kilogram, right? And mass of the, for example, arms, right? It's then 0.13 times 90 kilograms. And mass of the trunk and legs, right? So trunk legs is 0.8 times 90 kilograms. Okay. Now we can also have then the head, right? So head is kind of like a sphere with the radius of the head, let's say is 0.08 centimeters. Okay. And trunks and legs we can do as a uniform solid cylinder, right? With a a radius of, let's say, a trunk about 12 centimeters, so 0.12 meters. Okay. And arms can be modeled as, again, rods like this, where the length here is about 60 centimeters. So length about 60 centimeters or 0.6 meters length of arms. All right. Now, one of the things we can also do here is, since we're given 72 RPM, we take that, measurement in revolution. Remember, RPM is a revolution per minute. We want to convert that to radians per second. That means we take this and we multiply where 1 revolution is 2 pi radians, and 1 minute is 60 seconds. So we get omega as 7.5 radians per second, because we want this in terms of radians per second. All right. Then I calculate the moment of inertia. So moment of inertia total is moment of inertia of head plus moment of inertia of arms plus moment of inertia of the trunk and legs. So this will be 1/2 times mass. Sorry, think like this. So moment of inertia of head. Well, we said that head is a sphere. So sphere, remember, is 2/5 its mass times radius squared. So this is moment of inertia for the head plus moment of inertia of the arm. And arm was basically a uniform solid cylinder, and that was 1/2 mr square. So let's say this is mass of the head, radius of the head, and this is mass of the arms. No, sorry, this is the trunk. I guess let me kind of change it like this. So this is the trunk, legs, and this is the arms, like that. So then it's mass of the trunk and legs times radius of trunk and legs, so square. Plus the moment of inertia of the arms. And arms are rod rotating, right? So let's say, so we have things like this. So we have 2 of those, right? So one like that rotating at one end and another one rotating at the other end, right? So it becomes, 2 times 1/3 mass of arms and length of arms squared. All right, I'm kind of running out of room over here. Okay. Anyway, so let's do that. So 2/5 mass of head will be 0.07 times 90 times its size was 0.08 meters square, plus then 1/2 mass of the trunk and legs, which will be 0.8 times 90, then times radius square, which is 0.12 meters square, and plus 2 times 1/3, and we said the mass of the arms are 0.13 times 90, and times the length, which is 0.6 meters, 0.6 square. Okay, so we can calculate this to be 3.3 kilogram meter square. All right, so that was part A. Part B, then we find the rotational kinetic energy, which is 1/2 I omega square. That means I put moment of inertia 3.3, angular speed of 7.5 that we calculated, and we're going to get 93 joules. That means this is the rotational kinetic energy of the dancer as she's spinning at 72 RPM, okay, through her center with arms outstretched. Okay, you bring your arms closer, well, you have then less moment of inertia because your arms will no longer be, contributing into the, into this. And let's say, obviously, then you're going to have less kinetic energy to, for that particular case. All right, so here's one more example. And this example basically uses conservation of energy. Okay, so you have a solid uniform spherical boulder rolls down the hill as shown in the figure. Okay, so starting from rest when it is 50 meters above the bottom. Okay, that means we start from here, 50 meters above the bottom. That means we take this point to be our point 1, and the and this will then we're given that it starts from rest. That means I can say that speed at here at point 1 is 0. Okay, and you can say then position of point 1 here is 50 meters. Okay, the upper half of the hill is free of ice, so the boulder rolls without slipping. Okay, but the lower half is covered with perfectly smooth ice. How fast is the boulder moving when it reaches the bottom of the hill? All right, see, now we have something interesting. It says about halfway, right? So somewhere over there, our surface is rough. So our surface is rough, which means there's a friction. From that point on, there's a smooth surface, which is no friction. Okay. And what we have here is our problem becomes kind of, let's call this now part, 0.2, and then this is 0.3. Because going from 0.1 and 0.2, because there's a friction and we have a solid uniform spherical boulder, which means something that has a size, if there's a friction, it's going to start rolling. That means we have a rolling for that, going from 0.1 to 0.2, okay? That means here it rolls, okay? That means it's rolling, right, going from 0.1 to 0.2. But when it gets to 0.2, after that, it's a smooth surface. So what's going to happen? It's not going to roll anymore because there's no more friction. So it's going to slide. So it's going to slide going from 0.2 to 0.3. Okay. Now, what is the difference between, let's say, going 1 and 2 and 2 and 3? Well, kinetic energy going from 1 and 2 has a rotational part to that as well. Or going from 2 to 3, there is no rotational kinetic energy because it's not rolling. That means what we have here, we have to break it down into, going from 1 to 2, then going from 2 to 3 parts, okay? Because in order for me to find how fast it's moving at 0.3, I cannot reference 0.1 anymore because it's gonna have, let's say friction, right? Or it's gonna roll from 1 to 2 and then slide from 2 to 3. That means I'm gonna have to break it down into going 1 to 2 first. Okay, then find how fast it's moving at 0.2 and then use that for the second part. So let's look at then for this. Going from 1 to 2, what I can say is this: kinetic energy of 1 plus potential energy of 1 equals kinetic energy of 2 plus potential energy of 2. All right, so I know for sure that there is no kinetic energy at 0.1 because it started at rest. But there's a kinetic potential energy at there's a kinetic energy at 0.1. Potential energy at 0.1 because it's a 50 meter above the ground. So I'm taking then y3 equals 0. Then what will be then y2? Well, we are told that upper half, that means y2 here is 25 meters. Okay. Well, since it has a vertical position, there is also potential energy. That means what I get here is this: mgy1 equals, now kinetic energy, well, this becomes 1/2 mv2 square plus 1/2 I omega 2 square, then plus mgy2. Okay, because there is a component to that. So that means here, this is my kinetic energy at 0.2, both rotational and translational. All right, so then what I have here is I want to have just one type of system. That means instead of having translational and rotational, variables, I want to replace omega and moment of inertia with basically the linear values like mass and size, radius, right? And then, let's say, instead of omega, I want to have, linear velocity. And that's one thing we can do. For example, see what I have. So this is rotational kinetic energy, which is 1/2 I times omega square. Now, moment of inertia for a solid uniform spherical boulder is 2/5 mr squared, just a sphere, right, as we said. So it's 2/5 mass times its size, right, the radius square. And then we're using that v is equals to r times omega, or omega equals v over r, in this case like this, right? I can replace this with, that means omega squared becomes v over r square. Okay. And then from here, I can see, right, r squared cancels out. And I end up with, 2's and 2's cancel out. So 1/5 m times speed square. Okay, that means what I end up with is this: mgy1 equals 1/2 mv2 square plus, then this guy over here becomes that. So 1/5 mv square. So basically I end up with that. All right, 1/5 mv square. All right, so then plus mgy2. Okay, then what can we do here? Well, we can cancel all the mass everywhere. Okay, and then I can, switch the v's to one side. So 1/2 v2 square plus 1/5 v2 square equals then gy1 minus gy2, or we can just, factor it out. So g times y1 minus y2. All right. And what I get from here is adding those two together, going to give me 7/10 v2 square equals g times y1 minus y2 is just basically 25 meters. Okay. And then just solve for, basically solve for v2, right? Okay. So v2 is equals to 10/7. So let's say v2 squared equals 10/7 times g times 25 meters. So, but g, let's say, is just 9.8. And then I take the square root of both sides, and I get that. So then from here, what I will get is this. So this is v2. So I'm going to get 10/7 times 9.8 times 25. So then square root of that. So I get 18.7 meter per second. That means when it gets to this point 2, it's moving at 18.7 meter per second. And then from that point down, it's sliding down. Well, if it's sliding down from that point down, then I can say this is going from 2 to 3. What I have is this: kinetic energy of 2 plus potential energy of 2 equals kinetic energy of 3 plus potential energy of 3. All right. Now, one thing I know here is then there is no potential energy at 3 because that's my reference point. Okay. But I have kinetic energy and potential energy at point 2 because it has a speed at point 2, right? 18.7 meter per second, which we just calculated. And it has 25 meters, right? So this is 25 meters above the ground. So then I can say, all right, so then 1/2 mv square plus mgy2. Remember, this is the speed at point 2. Remember, at that instant, I can say that when it starts going this slide, starts sliding, right? All the energy here is just purely translational kinetic energy. That means there's no more rotation there. Then this is equals to then 1/2 mv3 square, which is kinetic energy at point 3. Again, I can simply cancel the mass from both sides. And, I can say, all right, so then 1/2. Or one thing I can do, I can also, multiply both sides by 2. So this cancels, that cancels, and 2 goes over there. And what I have here is this: v3 square equals v2 square plus 2 times gy2 by switching the sides, right? I switch the sides there. And take the square root of both sides. So v3 is equals to v2 square, which is 18.7 meter per second. Square that. Then plus 2 times 9.8 times y2, which is 25 meters. We'll do that calculation. So we're going to get 29 meter per second at the bottom of the hill. All right. So you can see, right? So, you know, kind of make this problem a little nice, you know, a little interesting by making half of the incline with, you know, rough, right, with friction. That allows the system to roll. But, you know, as soon as then it becomes smooth, right, you know, you have then basically just general, you know, from chapter 7, you know, like let's say a translational, you know, object sliding down, no rotation. But, you know, both cases you have conservation of, you know, mechanical energy. That means, you know, the only difference here is for the rough surface, you have both translational and rotational kinetic energy, where for the, you know, smooth surface, you have just translational kinetic energy.